Can you see the screen?
Yes, ma'am.
So we shall start the receiving end power circle diagram. What is that? From there, actually, circle diagram from the name it is clear that it will be a graphical approach through which we shall be able to assess the power system operation without rigorous calculation. That is actually the aim of the power circle diagram. So actually, this is mostly applicable or is applied to the receiving end at the receiving end side because we are more concerned about receiving end power rather sending end power. That means that what will be the receiving end power? What will be the condition to apply the receiving end power? That is actually our more concern. In that way, we shall send our sending end parameters. So that's why the stress will be given more in the receiving end power cycle diagram. So if we write the voltage equation using ABCD parameters, then Vs equal to AVR plus BIR. A and B are known from the transmission line parameters. We can calculate it. Now you know that VR is the reference phasor here, and A, B, IR, Vs all are the complex quantities. So if we write VR as a reference phasor, then angle of A and B are fixed. Say angle of A is alpha, angle of B is beta, and angle of sending end voltage is delta. Delta angle should be leading because the sending end voltage should lead from receiving end voltage to supply an active power. So from this equation 1, we can write the expression of current Vs by B minus AVR by B. So now if we can convert it into the complex quantities or in the polar form. So actually it will be this delta by beta is delta minus beta. In this way it will be Vs by B at an angle delta minus beta minus AVR by B into alpha minus beta. So this thing will come. Now, if we want to calculate the receiving end complex power, then SR is VR IR conjugate. Instead of VI conjugate, why V conjugate is taken? Because current is in algebraic form. That's why. So, in this expression, if the uh, imaginary part comes positive, that means it is the capacitive. If it is comes negative, then means it is the inductive one. So Vs are equal to VR conjugate into IR. So in that way, if we do the calculation, then SR will be this one. So this is the polar form. So from there, if we extract the rectangular form and separate in real and imaginary part, then we can get the active power and reactive power. In simple way, the cosine part will give you the real power and the sine part will give you the imaginary power. So this is the PR. Similarly, this is the PR. Now PR you see VRVS by cos delta minus beta AVR square by B cos alpha minus beta. Now if you see that if you can remember the transmission line parameters, alpha is the angle of A and beta is the angle of B. B is the impedance of the line. So angle of B or beta is far higher than alpha. So alpha minus beta is negative and delta minus beta is also negative because beta is near to 90 degree, delta generally within 30 degree, and alpha is near to 0 degree. So it is better to write it in a reverse way. So just you put cos of minus beta minus delta. So cos of minus alpha is cos alpha. So in that way we can get this equation 3. Similarly, imaginary part we can write in this way. Imaginary part, if we want to write in inductive form, because there is no numerical thing. So from the variable, if we want to write the imaginary power as an inductive one, then we must take the negative imaginary part because positive imaginary part will be the capacitive. So that means negative means we are writing the in inductive form. So that's why it is negative. So similarly, it will come within that. Now again, if we put beta minus delta instead of delta minus beta, then it will be like this. It is nothing but the mathematical manipulation. So finally, this will be the expression of QR. Now let us find out locus of SR when delta is only variable. We are assuming that if delta is varying, here in the equation 4, which are variable? VR, VS may vary or delta may vary. A, B, beta, alpha will not vary. So among these VR, VS and delta, we are assuming that magnitude of VR and VS are kept constant. Only angle between them are varied. That's why delta is variable. Then what will be the equations? So these are the equations. So then if we want to find out locus of SR with delta variable, then when we find out locus of anything, then we must omit the variable from the equation. Then we should omit the delta from this equation 4 as well as from equation 3, from this equation 3. Then we can get the locus of receiving end complex power, because receiving end complex power is a function of both P and Q. So from equation 3, we can write, we want to eliminate delta. So we are separating delta but from the others. So similarly, keyword is this one. Now if we square and add 5 and 6, you see in right hand side something constant into cos beta minus delta, and in the equation 6 something constant into sin beta minus delta. So if we square and add, then cos square beta minus delta plus sin square beta minus delta will give us 1. So we can eliminate delta in that way. So if we square and add, we can get this thing. So from there, we shall get this one. So this equation is independent of delta. So it is showing the locus of power when delta is variable. What will be the, if the delta is variable, then how P and Q will change, in which path they will move. Now you see, if P is X, then x plus something constant, x plus a, and this is y plus b whole square equal to some c square. So this is an equation of circle. So receiving end power locus will be a circle when delta is varying, keeping magnitude of VR and VS constant. So that's why it is a locus. That's why it is called power circle diagram. So it is written there. So it will be a constant circle. So what will be the center of the circle? X plus a whole square, y plus b whole square. So center will be x minus a minus b. So minus AVR square by b cos beta minus alpha, and y axis will be minus AVR square by b sin beta minus alpha. And the this thing we can write in polar form as magnitude of AVR square b at an angle beta minus alpha with negative sign. Why with negative sign? Because both of them has negative sign. Similarly, what will be the radius of the circle is VRVS by B. So if the receiving end and sending end voltage magnitude are kept constant, then the receiving end power will vary in a circle with radius VRVS by B and with angle with center minus AVR square by B at an angle beta minus alpha, right? Now see, I shall go here, come here later. So this is the thing, the center will be minus AVR square by B at an angle beta minus alpha, and radius will be minus VRVS by B, right? Now you draw with me that if then there will be two set of axes. If you have pen and paper and scale, then you can draw with me. Then if it is the two axes, then what will be two axes? Here the equation is p plus a whole square plus q plus b whole square equal to circle. Let me copy that equation here. Now you must you if we draw a set of axes, then the real axis will give you the active power P, and imaginary axis will have two sides. The positive side will be inductive, negative side will be capacitive, because we have taken PR plus JQR in the expression where in the starting we have taken started with inductive var. So inductive var we have taken here as the positive. So that's why it will be in the positive imaginary axis. Now you see, this was the center, this was the radius, and this was the equation. So the center is minus AVR square by B at an angle beta minus alpha. And then equation, the real axis is PR and imaginary axis is QR. So I have marked the real and imaginary axis, and center is O. So this is the origin of these two axes, right? Now the center is minus AVR square by B at an angle beta minus alpha. Then we must draw an angle beta minus alpha, right? And we must cut a straight line equal to AVR square by B in the negative side. That's why in third quadrant. If it would be only beta minus alpha, then we should draw in this side and cut minus AVR square plus AVR square by B from here. But it is in opposite side, so it will be in the opposite direction. It will be better if you draw with me. Then it is beta minus alpha. So from there, we must cut an distance equal to AVR square by B. Now, this point, the end farthest point of the this vector minus AVR square by B and angle beta minus alpha is O dash. So actually O dash is the center of the power circle and O is the center of the axis. So actually we are measuring powers megawatt and MVAR. So whatever we shall measure from O. O dash only the center of the circle. Okay, because the center is minus AVR square by V at an angle beta minus alpha. If the center be 0, 0, then it will be O, like that. Then radius is VR Vs by B. So with any radius of VR Vs by B, we must draw a circle. So this will be the receiving end power circle. Have you understood up to this?
Yes, ma'am.
Now you see, then every point on this spark circle are one SR, right? This may be SR1, this may be SR2 in this. And for different value of voltage, we can get different radius and different power circles, right? This radius will change if VR or VS changes or both of them changes, and center will change if only VR changes. Okay, so in that way there will be a set of circles. Now, so for at any point, say the power is SR, then this is actually the tip of the power. So this, if this power is on the receiving end power circle diagram, then only this power transfer will be possible, otherwise not, because this locus is giving the possible power power supplied by this transmission line, right? So what the real part, this is the radius will be obviously same. So this is, say the A is the operating point. Then obviously it is making at an angle beta minus delta with horizontal axis, right? So AVR square by B cos this is the beta minus delta, this angle OA, O dash A. Why? Because if you see, you cannot get it from this equation. But if you go to the original power equation, where is it? Yes, it is QR plus VR Vs by B, Vs by B sin beta minus delta minus AVR square by B cos beta minus alpha, sin beta minus alpha. So it had two parts. When we have converted to power circle diagram, then we have actually eliminated this one. That's why it is not coming in the equation. So actually, here this when we are calculating say reactive power, the real imaginary power, then it will have two part. One is AVR square by B sine beta minus alpha plus this VRVS by B sine beta minus delta. So sine beta minus delta means that angle should be with horizontal. That's why this angle is beta minus delta, right? So this part is the reactive power. Here it is inductive. And the real part is the active power. So this is the reactive power. How have I identified? Actually, SR is the phasor. So its vertical component will be the real reactive power and horizontal component will be the active power. Now you see here for any other value of SR. So this is say the SR, another power. Then in that case, this will be the radius. Radius will be same because it is on this power circle diagram. In that case, this will be the Q. Now you see QR is capacity because in the negative side and this part will be the P, right? And in that case, this will be the beta minus delta or delta 1, I may write. Now beta minus delta, if delta is increasing, that means beta minus delta is decreasing. So when delta is increasing, then actually radius will move towards the horizontal axis. And finally, it will superimpose with the horizontal axis, beyond which beta minus delta will be negative, which will not be possible. So power transfer will not be possible. This is one thing. Another is diagram, whatever I have drawn. Say we have a power of this much, requirement of this of the load. Then this is not in this power cycle diagram. That means this power will not be feasible to the supply by this power transmission line until and unless voltage is increased in such a way that there may be another power circle through it. So this is the application of power circle diagram. Here I have shown everything. So this side will be megawatt. So in numerical problem, when it is given to you, you must draw the indicate all the things. This is the megawatt. This is MVR, inductive and capacitive. It should be mentioned. And this is the center. O dash is the center of the circle, and O is the center of the axis. So every power should be measured from O. O dash is only to draw the circle diagram. And phi r is the power factor of the load, right? Now this is the receiving end power phasor. So P is this one, Q is this one. Now positive value of Q will indicate the inductive power. We have started with negative, then we have included negative sign within the expression. So this QR is including that negative sign because we have started with the V conjugate I. Anyway, so this equation 4, if it is comes positive, that means it is inductive, otherwise capacitive. Then in complex form, PR plus JQR, this will be the power. So the power actually, if it is SR at an angle phi r, so this will be the power. Now you see that positive value of phi r indicates the lagging power factor at the receiving end, right? So actually in polar form, if we shift the AVR square by B sine beta minus delta, angle beta minus delta and left hand side, then the equation will come. With this equation actually we have calculated, we have find out the expression of receiving end power circle diagram. So actually this is the thing in polar form, right? So in polar form, you see AVR square by B beta minus alpha. So this is the polar form. Then SR plus phi r. Then this is the SR plus phi r. That should be equal to VRVS by B cos beta angle beta minus delta. So how this beta minus delta angle is coming, that is justified using these slides. Because beta minus delta we shall not get from the power circle diagram because we have to eliminate that one to get the power circle diagram. So this will be the internal relationship of the power phasors, right? So actually this thing. Now you see, say there is a power sub to be catered is SR, right? So this SR power is to be catered. So for that there is a particular voltage, right? And this is the power circle diagram. SR may be supplied, may be catered with a fixed value of VR and VS. Say for this, the sending end voltage is VS1, say for example. Now say, so from there we can calculate what is the load angle delta 1. 1 minute. So this is the thing. So one thing, what is the application of power circle diagram? Say we have the requirement to cater the load SR. So to cater the load with the SR to with a receiving end voltage VR, sending end voltage should be set at VS. No, it may be possible that VS is readily available at the sending end, or it may be possible with the help of compensator we have to do it, either in the at the receiving end we shall adjust it. Compensation we have already learned. Here we shall use obviously shunt compensation, okay, because locally we shall adjust the receiving end power. So say somehow the voltage available is not VS1 but less than that, that is voltage is VS2, right? Something less than that. That means this A point is not within that power circle. Then this SR power will not be possible to cater when the voltage drops from VS1 to VS2, right? Now you see the active power is always same. If we draw a vertical line through A, that will give us the active power. Okay. So for the same active power A, if we want to supply for the new voltage VS2, then this will be the operating point. If you do not understand, you must tell me. So B should be the operating point, but B point is not possible because here inductive bar is this much and here is this much, right? Right? So actually, we have to shift the operating point from A to B by shifting the reactive power from here to here. Which reactive power? The QR. This is the QR. Is not it? On y-axis there is QR. So this QR you can easily compensate. So one inductive power bar, you have to make capacitive bar. Then how much compensation will be required? This plus this by shunt capacitive compensation. So this is the concept. Using compensation we can cater the same load even with lower value of sending end power. You must ask me if you do not understand, right? So I am repeating, when voltage drops then the power transmission may not be feasible. In that case we can get the corresponding active power requirement at what operating point, and the required volt reactive power we can uh, reach using the compensation, right? So in that case operating angle will change from delta 1 to delta 2, and the compensation required is this much, and this much is capacity because you are shifting from 1 to 2, right? It does not means every time when voltage drops the compensation will be capacitive. It may happen it is in between these two, right? So in that case compensation will be this much. Okay. So capacitive compensation does not means operating point should go to the fourth quadrant. It may be in first quadrant also. Even in this condition also capacitive compensation is required, but it is less than the previous one. So in that way we have to assess what is happening. So when voltage drops, obviously capacitive compensation will be required. This is shunt compensation, not the series, because we are directly reducing the receiving end power. Next is if the voltage rises, say rises to blue one, say Vs3, which is more than Vs1. Still, the VSR will be beyond the on the operating point of the this voltage power cycle diagram corresponds to Vs3. In that case, we have to shift the operating point from A to C. Then we have to increase the reactive power level. So in that case, compensation will be inductive. So in that way, using the compensation, and what will be the compensation requirement of the compensation, we can cater a particular load at different sending end voltage. Here you must remember, we are not modifying sending end voltage, but we are locally modifying the receiving end reactive power, so that same active power may be transmitted. In that case also, operating angle we can find out. Now always we are interested that what will be the maximum power transmitted by the line. So if we want to find out that, this is the equation 3 is the expression of power transfer through the transmission line. So here if we want to find out maximum power, then maximum power, and delta is only variable because beta and alpha are constant. So the condition is beta equal to delta, so that beta minus delta equal to 1. So in that case, the maximum power is this one, right? So at that condition, the reactive power will be this one. But reactive power is not maximum. It is the reactive power corresponds to PR max. Now, when we do this in our stability study, I do not know whether you have done or not. We assume delta equal to 90 degree, right? And beta, and for the normal operation, if delta equal to beta equal to 90 degree, why 90? Because it is impedance, angle of impedance more or less, so it is 90 degree. So it is 90, and for ABCD parameter alpha is more or less 0. So actually this expression come VR Vs by B sine delta, that I have derived in the last class for compensation, right? So actually this expression is derived, maybe derived from here. Here it is not required, but I have mentioned as it has come. But if we take the exact value of beta and alpha, so this will be the exact expression. So this is the QR for PR max. So if we draw the diagram, then this is beta minus alpha. So beta minus delta for a power circle diagram, say this was the beta minus delta. So beta minus delta is 0 means this will be shifted to the horizontal axis. So beta minus delta equal to 0. So this is shown by the purple color here. I am discarding this. So this is the beta minus delta equal to 0. So this is the point of P max. So this is the operating point. When this is the operating point, then this much is the Q. Q is some value, and it is obviously capacitive. So in this way, we can find out what is the maximum power transferred possible through a transmission line. Now you imagine when you have calculated in your power system planning and design classes for long transmission line for a particular voltage, if we want to find out feasibility of a power transfer, then you have to find out the ABCD parameter, then you have to calculate the sending end voltage, sending end power, then either calculating loss, or from the voltage regulation we can assess that if the voltage regulation or loss within limit, then this power transfer will be feasible, otherwise not. But from this method, using this method, we can readily say that whether it is available or possible or not, and what will be voltage regulation, what will be power loss, we can easily say. So this is very readily method. So what will be the compensation? So compensation, why it is applicable? Say actually it is blue dotted line. Say this was a power, right? So this was the power with this reactive power. Now, if we want to maximize the active power for this particular condition, then what shall we do? We shall shift this point to here. So the power will be maximum, and then compensation will be this much plus this much. So in that way, when the at the receiving end, the load is at a power factor angle phi r1 and it is drawing a particular load. If we want to maximize that power transfer, then we have to apply this much of compensation. Then this real power will be increased. Okay, or real power can be maintained because this much is the real power. And one thing you must know, that real power should be measured from the y-axis, not from o dash, because this vertical the axis with o origin are the axis set, and the x values are measured from the y-axis, so not from the o dash. So you should not make that mistake. So actually here I wanted to say that ideally if you want to transfer this power PR max, you need this much of Q. But leading bar, the load with leading bar is never happens in power transmission system. Generally, same load is required, but with some lagging bar. But same load with lagging bar is not possible to supply. Then we just supply that much of capacitive compensation. Then this point will be shifted here, so we can get same active power, that is maximum active power with some compensation. But what will effectively seen in the at the receiving end, load will be supplied the PR max at an angle phi r1, and with this much of inductive bar, and the capacitive bar will be drawn by the compensators, maybe synchronous condenser, or maybe the SVC. So this is the concept. Now one is the loadability of the line and compensation required. Say this is the operating point. So this is the radius, this is the power, and this is the circle. So at present the system is operating at a power, real part of power of SR. So SR cos phi r. If you do not understand, you must tell me. So SR cos phi r. Now if we want to maximize the loadability means the loading capacity of the transmission line, then maximum loadability is PR max. Then it is at this position, and it may go up to this. So loadability is, if it is PR max and it is PR1, then PR1, then PR max minus PR1 will be the loadability. Or in terms of delta, maximum delta possible is equal to beta. So loadability is delta max minus delta. That means how much load you can further give to the transmission line, right? So in this way we can assess the loadability, right? So this thing actually, now you see something, it is shown that it is asked that delta max will not be beta. The example I have shown that is to horizontal, but sometime delta max is not beta. So if the beta is 90 degree, delta max allowed is 60 degree. So in that case, what will be loadability? We have to find out P for the corresponds to that delta max, and we shall subtract from the available P. So that will be the loadability in terms of megawatt, or loadability may be in terms of delta also. Then delta max minus delta 1 will also be the loadability. So this is the concept of loadability. Now let us go through one example. My suggestion is I have given only one example with all possibility of the power system operation. You must do it in scale by yourself to make you understand. So three-phase overhead transmission line A and B are given. Select a suitable scale and draw the receiving end power circle diagram if the line supplies a load of this and this at 20 kilovolt at the receiving end, right? So at first, you see here receiving end voltage is given, sending end voltage is not given, but the power is given. So AB are given, VR is given, and so AB are given, so we can find out center. Now radius we cannot find out because Vs is not given. but PR is given. Now let us take the scale of 1 centimeter equal to 50 MVA. Then center will be converted to centimeter. Similarly, load is 50 megawatt at 0.95 power factor lag. So we can convert it into MVA, and again we convert it into the centimeter. Then receiving end power cycle diagram is shown by blue color, and A is the operating point. So how we have drawn? We have drawn 4.1 centimeter at an angle 45 degree, and this SR is 52.63 or 1.1 centimeter at 18 degree. So we shall reach the point O, right? So if we joint O dash and A, then we can get the radius, right? Now, if we get the radius, then that means in terms of centimeter, and if we multiply it by scale, then we can get that radius in terms of MVA. So we can get VR VS by B. So from there we can get the VS. It is asked that compute the following from the power circle diagram: sending end voltage, voltage regulation, operating load angle, loadability line of the limit of the line in megawatt if the maximum allowable angle is 70 degree. Let us go to the first. The receiving end power cycle diagram we have drawn. I hope you have understood. Now sending end voltage. So if the receiving end power cycle we know, then we can find out the radius, we can convert it into scale. Then from there we can find out VS, right? The next is, and VS here we have no need to convert into phase, line to line, because all are in directly in line to line, right? So the calculation is very easy. Then if we know the VS, then we can calculate voltage regulation. I hope you can remember voltage regulation is magnitude of VS by A, not of directly VS minus VR. Magnitude of VS by A minus VR by VR. So from here also readily we can say what is the voltage regulation, whether this voltage regulation will be feasible, well, whether we shall allow or not, or we shall increase the voltage level, that we can decide readily. Next is we have to find out operating load angle and loadability limit of the line in megawatt if the maximum allowable angle is 70 degree. Here beta is 76 degree, but here maximum allowable angle is 70 degree. So beta max is 70 degree. So from there we have to calculate. So initially we have to calculate operating load angle. Now you see we have got this one and this one. So beta minus delta 1, I do not know whether you can see it or not. This beta minus delta 1 you can measure. I have measured it is 64 degree. So from there beta is known. So delta we can calculate. Next, given delta max is 70 degree. So beta minus delta max is 60 degree. Sorry, 6 degree. So from, if we draw a radius with 6 degree, then we can get the PR max. So PR max is this much, and how much P is there? It is given PR max. I think it is asked for PR max. Okay, it is asked for PR max. So this is the PR max, right? Loadability limit. If it is asked for loadability, then it was 50 megawatt, right? 50 megawatt. So loadability it is 180 megawatt. So 180 megawatt minus 50 megawatt is the 130 megawatt would be the loadability. So you read the question properly and then answer. Next, another question using compensation. The same problem I had given, same data. Calculate graphically. This type of problem you have to do with power circle diagram, not using the ABCD parameter as you have drawn in your power system planning design class. The capacity of phase modifier. Phase modifier means actually compensator, because compensator compensate the power factor angle. To be installed at receiving end to supply a load of 80 megawatt, 85 power factor lag at the receiving end at 200 kV. While sending end voltage is kept fixed to 240 kV. What was the sending end voltage in our case? It was 220 kV. Okay. Now it is asked that sending end voltage will be kept to the 240 kV, and now we have to supply a particular load. Now, if sending end voltage, receiving end voltage, ABCD parameters are given, loads are given. So we can calculate everything, right? In terms of centimeter. Now you see when we draw the thing, you will see the operating point, the B is the, C is the required load. But this is not on the operating point, not on the power cycle diagram. B is on the power cycle diagram. So BC will be the compensation required. and from the circle it is the BC is the capacitive compensation. So in that way we have to calculate the capacitive compensation, and since it is reducing the inductive part, that means it is capacitive compensation. And you must remember it is not per phase, it is the total compensation, because we are calculating using the total power, not the individual per phase power. Now what will be the operating power factor in that case? Operating power factor will be the this one. This is the operating power factor at the load point. But what is the power factor of the load? Power factor of the load is this much. Have you got it? If you do not got it, then if you ask, can ask me. So power factor of the load and operating power factor are not the same thing. Then radius of the power circle diagram to cater the same load without compensation. So same load, this C. If we want to cater without the compensation, then we must add O dash C and find out radius, convert it into MVA. From there we can calculate VS. So in that way, this will be the sending end voltage. So if we want to operate, supply that power, 80 megawatt power with the voltage 250 kV, 240 kV, then we need this 25 MVAR compensation. If we want to avoid the compensation, then we have to increase the voltage level to 259 kV. So actually these are the applications of the power circle diagram. Maximum power that can be transferred to the line, so you can get the horizontal projection. This is come 249, 205 meter. This is the horizontal projection, this one 205 meter. Megawatt. Now let us concentrate on the equation of complex power at the sending end. So sending end, if you want to find out, in that case sending end voltage should be the reference phasor. All in our cases, whatever we have calculated till now, receiving end voltage was the reference phasor. Now, if we want to find out sending end voltage as the reference phasor, then we must calculate sending end voltage as a dependent variable on the receiving end voltage. So, instead of VSIS equal to something into VRIR, we need VRIR equal to something into VSIS. So, obviously, it will be ABCD inverse. So, this will be this one. So from there we can get the expression of VR, right? So from there we can get the current equations. All are complex quantities. So from there we can get the current equations. So from current equations we can get the complex power equations. Just multiply it. Separate real and imaginary part. Similarly, for varying delta, we shall eliminate the delta portion, beta plus delta portion. So this is the QS and this is the PS. So if we square and add, then this beta plus delta part will eliminate. So simply it will come this one. Now since we have done already very elaborately the receiving end power circle diagram, we can readily draw the sending end power circle diagram. So the radius is dVA square by B cos of theta minus R delta, right? And because radius is minus A minus B, so it is minus Q, so it will not no further negative sign here. And center is same, VR Vs by B as for the receiving end power circle diagram, right? So center is this much and radius is this one. So how we can draw? Here we must draw one set of axis, then this is say O, then center is dV square by B beta minus delta. Then we must draw an angle beta minus delta here. From there we shall cut dV square by B, right? Then this will be the center of the circle as O dash for the receiving end power. From there we shall draw a circle with radius VR Vs by B. Then this will give you the receiving and sending end complex power, sending end locus, right? Why I have drawn this arrow lesser than the center? Because you see center is dva square by b and radius is vs by b. Generally vs is far higher than vr and d is nearly equal to 1. That's why I have drawn in this way, right? So if we know the actual value, then we can do it easily. Now one thing you must note, this is the power point. So this is some sending end power. From where we shall measure? From the O. So this is actually power phasor, nothing to do with O dash. This is the power phasor. So real part will give you the PS and imaginary part will give you the QS, right? So this is the thing. You must do it yourself. So it's the same thing in detail I have drawn here, right? So this is the sending end power circle diagram. I think this is completed here. Okay, power phasors I have shown also, because here from here we cannot show what is the angle beta plus delta. It is not possible to identify. So if we write the power phasor just in phasor form, then we can get this is the S phasor equal to this phasor plus minus this phasor. So this phasor plus this phasor equal to this, or SR plus VRPS by B equal to dV square by B. So actually phasor relations are like this. So if this is the SS, then SS plus VRVS by B will be equal to dV square by B, right? And angle of the dV square by VRVS by B is the beta plus delta. So this angle will be beta plus delta, right? Actually, this angle will be beta plus delta because horizontal angle is the beta plus delta. Okay. So in that way, it can be justified. So this is the end of power circuit diagram. Power circuit diagram is quite complicated. You must do it yourself and tell me in the next class if you have any doubt. Otherwise, I shall skip to the next topic. You write your name and roll number in the chat box.